So if you recall, last time we talked about what a Reentrant lock was at a high level. We talked primarily about what a mutex is, and now we're going to start diving into the structure and functionality of Java's ReentrantLock class, which, as we'll see, has a very similar design with the semaphore that we looked at before. And we'll also talk about Reentrant mutex semantics, which is a cool topic. So what's the purpose of ReentrantLock? It's to provide a mutual exclusion mechanism for Java programs that's more flexible than the built-in synchronizer that you get with synchronized statements and methods. So it's basically a mutex for Java programs. The ReentrantLock implements the lock interface, which provides you with a very simple set of methods like lock, unlock, try lock, and so on. As with semaphore, it also applies the bridge pattern for exactly the same reasons. So you can have a common interface or common abstraction that when you invoke methods on, it'll forward to the appropriate implementation, which is either fair sync or non-fair sync. Under the hood, again, it's like deja vu all over again. It has the same basic structure as the semaphore. You've got a sync instance, a sync field that is an instance of the sync class, which extends abstract queued synchronizer. Abstract queued synchronizer is a framework that's used by various other synchronizers in Java that need to have first in, first out wait queues, where things kind of queue up to wait for stuff. And then we have non-fair sync and fair sync subclasses from sync. So this is just classic bridge pattern in Java. The constructor, like semaphore, again, this is very much the same pattern applied over and over again, has this parameter that's passed to it that lets you select whether you want fair sync or unfair sync. And it's the same as semaphore, same as Reentrant read-write lock for that matter. Fair sync gives you this strict FIFO ordering, which is fair but not as efficient. Conversely, non-fair sync is more efficient, but you can let threads barge. So it's not fair, but it's faster. By default, you get fast, not fair, because that's often what you want. And if you don't want that, you just pass in the true flag to the ReentrantLock constructor, which you'll actually be doing in your next assignment 2B. As a general rule of thumb, try to use non-fair sync unless you're told otherwise or unless you need to have it work in a different way. And in our program, we want to do it this way for various reasons. But in other cases, you don't really care. ReentrantLock, at one level, is very similar in its semantics with the synchronized keyword that you've got in Java, synchronized statements and synchronized methods that are part of the built-in monitor objects we've talked about before. So lock acquires the lock, potentially blocking until it's available. Unlock releases the lock if the thread that calls it owns it. There's also a bunch of extended capabilities. This is really what makes the ReentrantLock more useful than what you get out of the box with synchronized statements and methods. So we'll talk about these other mechanisms. So lock interruptibly allows another thread to interrupt the thread that holds the lock, and that will cause that thread to throw the interrupted exception. In contrast, Java's synchronized statements and methods do not support interruption. So they will just block until they get the lock, whether or not they're interrupted, which is a little bit annoying, right? Sometimes you want to shut something down and you don't want it to just sit there endlessly waiting to get something. You want it to be responsive and shut itself down right away. So lock interruptibly lets you do that. There's also several try lock methods. One that takes no parameters, and that will attempt to acquire the lock only if it's not held. That's very much like your try lock that you implemented for the spin lock for your, or Reentrant spin lock for assignment 1B. And then there's a timed version of this where you can wait up to a certain amount of time to try to get the lock. And if you don't succeed, then you'll get a false back. Java's synchronized methods and statements do not support non-blocking operations. They always block. Let's talk about Reentrant mutex semantics. As you might expect, because the class is called a ReentrantLock, it supports Reentrant mutex semantics, which is sometimes also called recursive lock semantics. So let's take a look at what it means to be a Reentrant mutex or recursive mutex. You can find out more about this concept here at the Wikipedia link. So the way this works is if you own the lock, then when you, the thread that owns the lock, if you're a thread that owns a lock, if you come back around again and try to reacquire the lock, it will simply increment a count by 1 rather than deadlocking on itself. whereas a non-recursive or a non-reentrant lock would deadlock on itself. Very, very bad. But, as we'll talk about in a second, reentrant semantics are more expensive to implement than non-reentrant semantics. Non-reentrant semantics can typically be done with a simple hardware instruction, so it's super fast, whereas reentrant semantics take more work, as we'll see. So that's the basic idea. If you own the lock and you try to reacquire it, it just increments a count by 1 and continues on its merry way without having to block at all. Okay, here's what the code actually looks like if you were to go look at the source code for ReentrantLock. This is what the code that gets called to do these semantics. And I'm not going to go through this in gory detail, but it is actually quite interesting to see what it does and how it works. So what it does is it comes in, and you can see it stashes the current thread in a local field. And then it gets the current state of the lock, which is just this count. And if the count is 0, which means nobody owns it, very much like your spin lock, right? If it's 0, if it's false, then it tries to call compare and set, trying to go with setting 0 to whatever you're trying to acquire. Let's say it's 1 for sake of argument. So if it's able to go ahead and switch that integer from 0, meaning it was available, to 1 or n, where n is the acquires parameter, then we've got access to the lock, and we set ourselves as being the thread owner for this thing. And we return true because we now own the lock. Otherwise, if we are the current holder of the thread, in other words, the count was greater than 0, and we're the thread that owns it, that's what this check does, then we simply go ahead and increment the current count by the number of permits we're trying to acquire, or the number of things we're trying to acquire. Let's just assume 1 for a reentrant lock. I'll explain why this is generalized in a second. And then we call set state, and that sets the count to be whatever this new update value is. And then we return true. Otherwise, we return false, which means it's currently locked. The reason why we have this acquires thing is because non-fair try acquire is used both by semaphores and by reentrant locks. The difference, of course, is reentrant lock only allows increments by 1, whereas semaphores could allow increments by multiple permits at a time. Okay, so that's basically the implementation of it. It's really cool. And for the grad version of the course, we actually had people implement a reentrant lock, as a reentrant spin lock, as opposed to just a non-reentrant spin lock, which is what the undergrads did. At some point, not today, but at some point I will walk through my solution to assignment 1 so you can kind of see how I did it, and you'll see what it looks like for both grad and undergrad versions. The version that's written, that I wrote, is a little bit cleaner than this. This is really written to be very low level, but it works quite well. So let's take a look and see when reentrancy might be useful. And it's primarily useful if you have object-oriented frameworks where there are callbacks that take place while locks are held. So what would be an example of that? Well, it turns out that there's a class called a countdown timer. And a countdown timer, as the name implies, is set to some value, and then every period, whatever the period is, it will go ahead and call back on a hook method saying the tick is the next tick has gone down. So as an example, you might say, for the next 30 seconds, once a second, call me back. Right? So you can imagine having some kind of GUI program on your phone or whatever that does like a stopwatch, and it'll count down from some number to 0. So that's basically what this thing is doing. So you have a countdown timer, and it's got methods called start, on tick, which is a hook method, on finish, which is when you're done, and cancel. Those are the methods that are part of the countdown timer interface. And when someone goes ahead and starts this particular method, and the countdown timer starts to run, it's going to acquire the lock because we don't want to have its state corrupted. And every so often, it's going to call the on-tick hook method. So again, let's assume it's 30 seconds, once a second. Once a second, it'll grab the lock, call on-tick. Well, let's take a look at what on-tick might do. So on-tick might decide, I'm done with my countdown. I'm not going to wait till I get to the end. I'm going to stop it at this point. Let's say I'm going to count down till something happens, and that thing happened. So at that point, I stop. So in that particular case, this method on tick, which is a hook method implemented by a user to do user-specific code, is going to call the cancel method on the countdown timer. So remember, the lock is held, on tick was called, on tick calls cancel. So now let's go take a look at what cancel does. Cancel needs to ensure the lock is held. And the reason for that is that another thread that's not being called in the context of on tick can try to cancel the timer too. So you need to make sure that no matter how cancel is called, it always acquires the lock before it starts trying to muck around with the internal state of the countdown timer. So what it's going to do in that case is it's going to set the mCanceled flag to true, shut down the service executor, the scheduled executor service, and so on. So the key point here is we have to reacquire the lock, and this lock is already held. So if this is a Reentrant lock, which it is, that works perfectly fine. If it was not a Reentrant lock, we would deadlock on this call to lock. So the point here is that Reentrant locks are particularly useful in object-oriented frameworks where callbacks take place while the locks are being held. And you call back into the framework, into the object to do something. Any questions about that? Yes, Sarang. Oh, great question. So you can actually see that. I don't actually highlight this, but we can talk through it. So cancel gets called. So lock is held here. So the count will be 1 because it's locked. Then on tick is called back. On tick calls cancel. Cancel acquires a lock. Now the lock count is 2. When it's done with this piece of code, notice that no matter what happens here, we unlock the lock. So the lock is turned into a count of 1 now. Then on tick returns, and then we unlock the lock. So it'll drop back to 0, and then it'll go ahead and release it. Yeah, great question. Okay, so that was just an overview of kind of the structure and functionality of the Reentrant lock.